We move to the next talk, which is by Ali Alpar, who will speak about neutron star dynamics on the time-dependent external torques.
Okay, hello everyone. I will now take you from the magnetosphere to the neutron star. So far the discussion has been about outside the neutron star, the external radiation processes, external torques, and these are directly coupled to the crust surface of the neutron star. But the neutron star has interior components, and it has to exchange the angular momentum with those interior components. This is work together with my colleague Erbil Gügercinoğlu. Okay. Now, in the early years of pulsars, as you all know, immediately after the discovery, the Vela and Crab pulsars showed glitches. First Vela glitch were discovered by Radhakrishnan and Manchester and Rashdi and Downs, and immediately it was something interesting because the pulsar was suddenly jumping in rotation rate as well as in spin down rate, and interestingly this jump showed partial relaxation. First, it was discerned as exponential relaxation, and the relaxation times were unusually, unexpectedly long for any normal viscous fluid. So, in 1969, the two-component model was developed, very simple model. So these equations okay, we have two equations. I'm assuming that, the two-component model assumes that the neutron star, of course, has a crust rotating at the rate omega c, and it has some component. Let's assume just one component, a superfluid component. So the total loss of angular momentum of the system with the two components is determined by the external torque on the neutron star. Now, the crust or normal matter rotation rate, what does it do? Well, it should obey the Navier-Stokes equation with viscosity. Its time scales for neutron star or any star viscosity parameters are very short compared to the observed time scales. What I mean by the observed time scales is the time scale of the exponential relaxation, which is like hours, days, weeks, months, and the time scale of repetition of glitches and nonlinear relaxation between glitches. So those also extend in the Vela pulsar to a couple of years. Compared to that, the Navier-Stokes equation does its work immediately, and in fact we see no effects of most of the star on time scales observationally longer than 40 seconds. So essentially this crust contains whatever interior components of the star exist that have coupled by fast processes already, and the superfluid here is a superfluid component that is observed to be still relaxing after the glitch. Okay. Now, how does the superfluid relax? The two-component model posited that the superfluid spin-down rate is linear in the lag between the superfluid and crust rotation rates. So this little omega is my notation for the lag. And what is physically behind this is a superfluid carries rotation in discrete quantized entities in vortex lines. And to change its rotational state, it must support a current of these vortices. If the vortices manage to move out, then the superfluid will spin down. How do the vortices start to move out? Well, they have to interact. Cores of the vortex lines are normal matter. They are interacting with, for example, the electrons, which are very rigidly coupled with the crust, and that imparts forces on the vortex lines, and the resulting motion of the vortex lines is in the radially outward direction, etc. So the whole process goes back to what the forces are between the vortex line and the ambient normal matter electrons. And for many physical mechanisms, those forces indeed are linear in the velocity difference, like ohmic forces. Okay? And that then eventually gives you a flow of vortices. This is also linear in the lag, and therefore the spin down rate is linear in the lag. And of course, this coupling time there, relaxation time there, contains in it all the physics. Okay. So this kind of system, of course, has a dynamical steady state, which is reached when both components are spinning down at the same rate. What rate is that? Well, that is, of course, dictated by this equation, by the external torque. Okay? And corresponding to this steady state, there's a steady state value of the lag, which you can easily work out from this. Now, a glitch comes, and as we observe, the crust rotation rate is suddenly perturbed. So if the system was in steady state before this observed event, now it is no longer in steady state. Depending on your model for the glitch, the superfluid rotation rate may also have changed suddenly at the glitch, but that's model dependent. In any case, the lag has changed, and in a linear system, the solution of this simple set of equations is exponential relaxation. So this is very important. A linear system means exponential relaxation. Exponential relaxation is linear response. It's of course linear in the inertial parameters, in the moments of inertia, but the important thing is the response, the amplitude of the response is linear in the offset from steady state, and the response itself has the familiar exponential relaxation form. Now, directly from the observations, the offset in the fractional change in the spin down rate that you observe after a glitch is typically 10 to the minus 3, at most 10 to the minus 2. That's just an observed number, delta omega dot over omega dot of the crust. That corresponds to the moment of inertia fraction in the superfluid. And in recent years, Nicolas Chamel pointed out that it's not that straightforward, because the effective mass of the superfluid neutrons in the crust may not be the same as the bare mass. And if you take that into account, then the actual moment of inertia fraction that you extract from the data with Nicolas' idea may be up to something like 10 to the minus 1. But the important lesson here is this fraction here is always a small number. And that's good for us because the two-component model is enough. What does that mean? Well, there are different layers of superfluid inside the neutron star. Maybe they have different coupling times. So it's really like there's IS1, IS2, IS3, and should I have a multi-component model? I would have to do that if they all had comparable moment of inertia fractions. But if the whole thing is limited, as the observations show, to few percent changes, then in addressing the data, I indeed observe several different relaxation times, but I can take them one by one in coupling to the rest of the neutron star, and then I can put it back together in terms of what the response does to the behavior of the observed crust rotation rate. Okay? Now, in the early 1980s, it was already realized after the first 4 Vela glitches that exponential relaxation was not the whole story. There were several exponentially relaxing bits, and when those were over, after a month or so, the system was still not relaxed, and it kept responding to the glitch with a power law. Okay. Power laws means nonlinear dynamics. Okay? And we had a simple explanation for that, because one expects in the neutron star crust the superfluid is interacting with a very inhomogeneous medium which can pin the vortices down. And if you say, well, what will happen? Well, this is at finite temperature. Any pinning energy can be overcome at some rate with thermal activation. So one can build, when there's a lag in rotation rate between the superfluid and the crust, what is going to sustain a mean outward flow of vortices. That's called vortex creep. And we had a simple theory for that. And for our purposes today, the important thing is now the spin down rate of the superfluid has an exponential dependence on the lag. And you go back to the 2-component model. Now we have a nonlinear version where the spin down rate is not just minus omega over tau, it's some nonlinear function of omega, in fact an exponential function of omega. Of course, there is still a steady state of the system, and one can calculate properties of steady state, and one can calculate a solution. So if a glitch comes along, both the crust and the superfluid rotation rates are offset, the system is now going to respond to that. The response is quite complicated, but I'll show you a picture. There are 2 time scales here. One of them is the relaxation time for this nonlinear process. This is directly proportional to the temperature. And the other one is the recoupling or waiting time. What does that mean? Well, if you offset the lag by a certain amount delta omega, the superfluid will stop doing anything. But there's an external torque, and that is spinning the pulsar down. So the crust is spinning down, and that's going to rebuild the lag. And after some time scale given by the initial offset, divided by spin down rate that you observe, the system will go back to steady state. This is the idea. Now we went back to the problem of what the Vela is doing recently with Onur Akbal, Sarah Buchner, and David Pines, and I'll take you to that paper to show what I mean by the nonlinear behavior. First, this is from a very old paper in, I think, 1984 of the model of vortex creep. It tells you that it's such a nonlinear sensitive coupling that when the glitch happens, it takes the system off from steady state. The superfluid stops doing anything for a while. It's totally decoupled. That means you have the same external torque acting on less moment of inertia, so you see a jump in the spin down rate. And this will stay like that. The superfluid is totally out of the picture until a waiting time, and you expect a step recovery. We predicted this, and in a subsequent glitch of the Vela pulsar, it was observed here. Okay. Now, what is more common, as Dick Manchester also showed, and now we have 17 glitches, so we went back to the problem and applied the model to all of them. The standard thing that happens between 2 glitches after you subtract the initial exponential relaxation is that the system, I am plotting omega dot versus time, recovers at constant omega double dot. Okay? So we have power law behavior. The reason for that is different parts of the superfluid have different waiting times. So you can imagine little bits come up and recover in little steps like that. And this constant second derivative corresponds to the simplest thing that can be regarding the distribution of vortices. I won't go into the details of that. But this is very systematic. After every glitch in the Vela pulsar and other pulsars where you have data like this, you see this nonlinear behavior. Okay. Now, all these years we applied such models to radio pulsar glitches. Then magnetars came along, and before that, of course, we had the high mass X-ray binaries, and high mass X-ray binaries with the accretion torques around are very variable. And then magnetars came along with some affiliation, obviously, with radio pulsars, but again, they had very rich timing behavior. Okay, so and magnetars also showed some events, some of them similar, some of them a bit different from pulsar glitches. So one has to consider what happens if the external torque is variable. Until last year, we didn't need, because we were working on radio pulsars, to consider an external torque that's variable on month or year time scales of the observations. On those time scales, the pulsar torque is constant. Well, it turns out, even though we had never bothered to look at this problem, if you put in an external torque that's time dependent, the two-component model is integrable. For both the linear case, which I'll show first, okay, what happens is you have here the observed spin-down rate of the neutron star crust is just mimicking the external torque, lowest order. Then to order 10 to the minus 2 or 10 to the minus 1, you have an extra term which depends on some transform, some integral of the external torque history. So the obvious strategy is one would make a lowest order fit, and that will tell you what the external torque is doing, and then the residuals should be of order 10 to the minus 1, 10 to the minus 2 compared to this term. And one can, in principle, check for the consistency because the function you have derived here feeds into this integral. Okay. And I'll show you quickly. That's rather simple because for simple kinds of things that you expect in the external torque, like if there's a transient thing happening in some accreting source, fast rise, exponential decay, as we observe in luminosity, you make the hypothesis that the external torque is doing a similar thing, and then you can integrate, and it's very simple, to extract from the data what the decay time scale of the external torque is in comparison to that of the internal. One can do the same thing if there is a power law variation, arbitrary power law. You can integrate in the linear two-component model. Okay. For noise, we tried white torque noise. This incidentally had been done a long time ago by Lam, Pines, and Shaham, and later by Altan Baykal, myself, and Ümit Kızıloğlu, with some other point of view. But if you bring this into our integrated solutions and put in time-dependent torques, again, you work the power spectrum. The power spectrum to lowest order is the power spectrum of the external torque, and the next order will give you a higher order power spectrum, but it is like 10 to the minus 1 or 10 to the minus 2 suppression. And again, you can check for consistency between these two because there is specific prediction, and you can try to extract various parameters of the noise process. And you can do the same, for red noise, random walks, whatever. Okay. Now, if you take the nonlinear two-component model, with the specific case that the coupling is exponential in the lag. That happens to be integrable easily. So you at least have a closed form. Things are a bit more complicated. I won't really go through it. Just point out that for vortex creep process, for this nonlinear thing, if the external torque is arbitrary, you can put in the external torque function and figure out the effect of the response of the neutron star interior. And again, we have the same feature here. Sorry. We have the same feature. To lowest order, you just take your spin down rate time series that you observe and read off from there what the external torque time series is, which will be very promising when we start applying this to magnetars and high mass X-ray binaries. You can read off the external torque. And then you can check for consistency, because the higher order term then contains some more complicated transforms of the time history of this external torque. Okay? We have just submitted this for publication in monthly notices, and we will then try to apply this to data from magnetars and high mass X-ray binaries. Thank you.
Questions? Jason?
Have you thought about applying this also to the transitional millisecond pulsars? Because what's interesting there is on a few minute time scale, the accretion seems to switch on and off, and we know this because the accretion-induced pulsations switch on and off as well. So I'm wondering, and for one of these systems now, we also have during the accreting stage a phase coherent timing solution as well, so we can quantify the amount of timing noise in there as well. So it might be able to make some prediction about how well the crust and the core are coupling in those types of systems as well.
We should do that. I mean, you know,
yeah, I can
if
show
you
you
have the time series and you give me a time series of omega dot that's observed, then we can just put it into this machine. And for simple forms, we can check directly, and you know, we can.
Yeah, I think that would be another really nice application.
Yeah, thanks for the suggestion.
Some other questions? Well, if not, thanks again, Ali.
Thank you.